Let's take a look at how to define and select a data transform in ProRaster. I'm using ProRaster Premium. So in an algorithm you'll have lookup table color layers and RGB layers and image layers. So the color component requires a data transform. In the red, green, blue layer, the red, green and blue components require a data transform. And in any layer, the opacity component will require a data transform. So defining data transforms is a big part of what you do in ProRaster. And there are three ways to do it. So in order to define a data transform, you'll go to the color page or red, green, blue page, go to the color page here, and then you have a data transform type, which has a long list of different transform categories. And when you select a transform type, you'll then get a data transform member, and you can select a specific transform from here. So that's how you'll select your transform from these two buttons right here. That's the entire story. However, where the data transforms come from is a different story, and there are 3 or 4 different ways that you can acquire a data transform. So the first one is to go into the data transform editor. So in the editor dialog, you can create data transforms and you can save them, give them a name, and then you can use them thereafter. They get stored onto your hard disk, and in any algorithms that you create, you can reuse these transformations. So that's one way to do it, and that's sort of an advanced way to do it. The second way to get a data transform is via color tables. And in the color table editor, we have our system color maps, and we have our user-defined color tables, and then we have the external folders. Now, in ProRaster, we support the extended lookup table color format, and that can be defined with just color or with color and a data map. We also support legends. Legends, by definition, have a data map as well as color. And we also support for read-only a number of other color table formats, and some of those support data transforms as well. For example, some of vertical mapper formats. So your data transform might come from a color table. Thirdly, there are a whole bunch of kind of standard transforms, system transforms, and mostly represented in this top section from no transform down to ranges. And you can select any one of these and select a member. You might get some parameters that you have to fill in. For example, if we go to a linear transform with a manual clip, we'll need to put in the clipping parameters. And that becomes a standard transform, and they can be created on the fly and very easy to use. So that's the third way. And then finally, if you load a algorithm, it might have a transform in it that the system doesn't recognize. In other words, it doesn't match any system transform. It doesn't match any transform that's been saved by the data transform editor dialog. And so it will then appear, if I go to this one, for example, if we go to the color page here, it then appears in this category called local transforms. Normally you won't see this, but it will pop up if you load a transform from an algorithm off disk that it can't match to anything that it's got in its system. So, what does a data transform do? Well, it's kind of a 3-stage process. So we have to get from data to a color that's acquired from a lookup table. And the first stage, we use a function to transform the data from data space into a scaled data space which is between 0 and 1. Then in the second phase, we scale that data up to into what we might call index space, which is usually between 0 and 255. It's the number of colors that are in your color table. And then in the third phase, we use that index to go and acquire a color from the color table, and that's used to color the pixel. So let's take a look at the standard data transforms. So we'll go firstly to an RGB layer, and I'm displaying an ECW here. If I want to display imagery without any color stretch, well then the first thing you do is you use an image layer. But if you're not able to do that, for example if the color in the raster is split into red, green and blue bands, so you need to recombine them using a RGB layer, then go up to No Transform. And under No Transform there are 4 options: pass scaled, index and value. So these first 3 pass values through with only a limited number of transformations. So in the first one, pass scaled, we assume that we've already got numbers between 0 and 1. So there's no initial transform function. Pass index assumes that we've already got numbers that are between 0 and the number of colors in your color table. So we don't need to do anything but use that index to look up the color. And then the third one, we assume that we've already got the color in the raster and we just need to pass that color straight through without modification. The fourth one is like pass index, but it rotates the index. I have an example of this. So this can be used to display sort of pseudo-random coloration of things. So here we have a classified raster, which has all the countries in the world in it. So there's like 200 odd entries. And I'm using rotate index, and I'm rotating it through 16 colors. So the index is going to be between 0 and 15, and when the input data is greater than 15, we get the modulus of 16. We have a 16 color table, and that gives us this kind of pseudo-randomized display where each country gets a different color. So let's go back to our red, green, blue. So that's our No Transform. For color data, we can choose color transform. This is quite handy. This is essentially a linear transform, and all you have to do is specify how many bits of color information you have, and it will usually be 8, which means you've got values between 0 and 255. If it was 10, you'd have values between 0 and 1024. So that's another way of acquiring something with no stretch. And that's how you treat color data. If we go now to, let's have a look at terrain data, go into color. After the color transform, we have the linear transform. Now if we look at the members under the linear transform, there's pure linear, and then we have these percentage clips, and then we have percentile clips, and then there's a manual clip. And this is pretty much the same throughout all of the different transform types. So in the first one, pure linear, the system needs to define the minimum and maximum value over which that linear transform will be applied. And when you don't specify that value, it's going to use the statistics of the raster, and it'll find the minimum and the maximum, and that will be the limits of your transform. If you choose one of these clip options, it's going to clip the bottom and the top by the percentage or the percentile indicated. And when it uses percentile, we're talking about using the histogram data to work out a quantile. And so you get a statistically derived clip at the top and the bottom of some percentage or percentile. If you want to define your clip manually in data values, then you can do it here. So for example, I might only want to stretch from 5,000 meters over to 3,000 meters. Oops. Hit return, and that gets applied. So now we have, now everything below 500 is going to be deep blue. Everything above 3,000 is going to be this vivid red, and the color stretch is all in those areas between 500 meters and 3,000 meters. So that's our linear transform. Logarithmic transform is a little bit different. It also has a manual clip option, but it doesn't have the percentage and percentile clip options. That doesn't mean you can't use them. You can use them via the data transform editor dialog. Instead, it's got these various options for the transition point. So a logarithmic transform, to handle 0 and negative numbers, Firstly, it needs to make negative numbers positive, do the log, and then make them negative again. And at 0, it can't handle it. So the transformation allows for a small portion of data to be treated linearly, and that's between plus or minus some value. And here's the values here. So plus or minus 10, plus or minus 1,000, plus or minus 0.01. So if we go into 100, for example, we get a better stretch with logarithmic. Equal area transform is a histogram derived transform. So it uses the histogram to try and make sure that every color in the color table is represented by a similar number of pixels in the view. And so in other words, we get the best possible stretch of the color and use of our color. We have all the clip options as well as the manual clip. When you choose equal area, you get this additional control, and this allows you to dial up or down this transformation. So if I set this to 0, I get what's equivalent to a linear transformation. And then as you bring that up from 0 to 100, it transitions from linear to equal area. And so if you find that your equal area is causing too much contrast in your imagery, then you can use this control to just dial it back a bit. But by default, it's set to 100 and you get a pure equal area. So our next one is a stable equal area. It's exactly the same, but it's treated differently. It uses different histogram data and it uses a different technique. It renders a little bit more slowly, but it is very resistant to outliers and to highly skewed distributions. So I'll just give you a little demonstration. So I've got here some, so we'll go to equal area transform, zoom in. So this is some hydrology data, and we're seeing some creeks and rivers here. So you can see that most of our creeks are blue. So this is a very highly skewed distribution. If I change it to stable equal area, suddenly the whole picture changes and I've got color gradation along my creeks all the way through. So we've got a much better color distribution using stable equal area, and that's because it's able to handle those really nasty skewed histograms better. So we have sigmoid lightening, and there's also a sigmoid darkening, and let's go to something where we can see that. Just go to the lookup table. Sigmoid lightening, so we have here all the standard clip options, manual, percentage and percentile, same with sigmoid darkening. Sigmoid function ranges between a linear function and a curve. So it's so if the curve bends upwards, then you're getting some lightening. If the curve bends downwards below the linear transform line, then you're getting darkening. And the amount that it curves is given by this, and you can put it between 0 and 100. So when you're on 0, you're linear. When you're on 100, you're on full upward stretch, which doesn't make much sense. But you can bring that curve back, just dial it back to whatever you want. And sigmoid transforms are useful with satellite multispectral in particular. But generally, they're quite useful transforms on their own. Finally, in these system transforms, we've got ranges. So now we're talking about generating a specific number of ranges, generally relatively small number of ranges, 8 or 16 or so. And so we need to define the data top and bottom for each one of those ranges, and there are a number of ways to do it. So firstly, it'll be done based on percentages, and so if I have 8 ranges here, then it's going to equally divide the data up between the minimum and maximum and create 8 ranges. If I use a manual clip between 0 and 5,000, then I get a better looking display. Go back to ranges. See, that one is a bit Doesn't really work very well, but we clip out some of those low-level data and really high mountains, then we get a better looking range. And this is the number of ranges you have here. So we've only got 8, so it's gone in, and this color table has got 1024 colors, so it's gone in and picked out every 128th color from that color table to populate the range. So our manual quip, we have quantile ranges. So now we're not dividing the data space based on just simply the percentage. Now we're basing it on percentiles. We're using quantiles from the histogram to determine where the range boundaries should be. And you can see that it looks more like an equal area distribution now. And then we have some fairly specific ones. We have ranges spread about the mean, the median, and the mode. So these are all percentage-based ranges above and below this specific value, the mean, median, or mode. So when we have 8 ranges about the mean, that means we have 4 ranges above it and 4 ranges below it. And that's based on statistics, so the width of each range will be different above and below the mean. Deviations about the mean. So now we're centering our ranges on the mean. We have 8 ranges, so there are 4 above and 4 below, but the width of the range is equal to 1 standard deviation in every case. And finally, we have the Jenks natural breaks. So this is an algorithm that examines the statistics of the raster, looks at the histogram, and works out where the best place is to put the range breaks and generates however many ranges you want. And that's quite a handy algorithm as well. So that's all of our standard data transforms. From there, we go into all of the stored transforms that you've created through the data transform editor and all of the color tables. Okay, so we go into stored transforms. Now we see a list of the transforms that you've created via this data transform editor dialog. I've only got one linear top percentile clip. If I go in here, here it is listed, and I can select it. Then we have all the places where you have color tables where you might have data maps in those color tables. So that will be from the system color maps, and in here we list all the color tables in there. It will be from any external folders that you've linked to using the color table editor dialog, and it will be in your user defined color tables. And in there it will find the ones that have maps in them and present them as options. Finally, if you load an algorithm that has a data transform which doesn't match any of the system transforms or any of the color tables, then you'll see a new category pop up here in the data transform type list, and it's called local transforms. Under local transforms, we have the transforms that are loaded from this algorithm, and you can select them there. So that's a brief introduction to how to select a data transform in ProRaster.